Right. Thanks for coming to my talk. This is joint work with Anurag, Anshu, David Gosset, and Karen Morenz Korol. So David is the chair, and Karen is also attending the conference in person if you'd like to talk to them about this work. So let me begin with some background information. Suppose we have n qubits that are interacting with each other via a local Hamiltonian that I'm going to assume it's 2 local for now. And this Hamiltonian involves m local terms. And as you see, we can assign an interaction graph to this system with n vertices and m edges. And one important assumption that I'm going to make about this graph is that its degree is at most p, meaning each qubit is interacting with at most p other qubits. And although I'm going to restrict myself to 2 local Hamiltonians for now, later I'll show you how all this generalizes to the k local case. So this Hamiltonian has a spectrum. And in particular, its eigenstate with the lowest eigenvalue is called the ground state, and its eigenvalue is called the ground state energy. And we know from statistical mechanics that many low temperature properties of this system can be obtained from the ground state. And because of this, we'd like to have algorithms that, given the description of the Hamiltonian, compute these properties for us. But on the other hand, it's also generally believed that obtaining these properties of the ground state, in particular the ground state energy, is a problem that in general requires computational resources that scale exponentially with the number of particles. So let's look at this exponential hardness in more details. I'll first tell you about the worst case complexity and rigorous algorithms, and then I'll tell you about heuristic quantum algorithms. And as you'll see, our work relates to both of these topics. So let's start with the worst case complexity first. And as I mentioned, our goal is to, given the description of the Hamiltonian, obtain the ground state energy, which is the smallest eigenvalue of the Hamiltonian. So it's known that estimating this ground state energy within an inverse polynomial additive error is QMA hard. And turns out even obtaining cruder approximations could be computationally intractable. So this is the consequence of the PCP theorem, the probabilistically checkable proofs theorem, which says that there exists a constant epsilon such that it remains NP hard to estimate the ground state energy in the worst case within an additive error epsilon times m being the number of local terms or the norm of the Hamiltonian. So whether this NP hardness can be improved to QMA hardness is an open conjecture. But in the physics language, what this says is that for sufficiently small extensive errors, it remains, or it might remain computationally intractable to estimate the ground state energy. So given this computational hardness, we can ask what is the best approximation of the ground state energy that we can obtain using efficient algorithms, meaning algorithms that run in polynomial time. So this has been studied before. There are various known algorithms for this problem that come with rigorous performance guarantees. So we know this when the local terms of the Hamiltonian are Heisenberg-like, or when they're positive semi-definite or traceless, or when we have restrictions on the interaction graph, like when it's assumed to be dense or planar. So one common feature of these rigorous algorithms is that they output a product state at the end to estimate the ground state, meaning either a tensor product of single qubit states or a tensor product of few qubit states, like a bunch of Bell-Purse tensor together. But on the other hand, we know that the ground state of local Hamiltonians could be highly entangled. So the question that arises here is that what is the structure of states which provide good approximations to the ground state and can be efficiently computed? So for high degree graphs, turned out product states do provide good approximations to the ground state. And the intuitive idea behind this is the monogamy of entanglement, which says that 2 qubits or qubits that are highly entangled with each other can't be also entangled with other qubits. And this is the basis of the mean field approximation, which is a widely used method in the classical simulation of interacting quantum systems. So this idea has been formalized before in a work of Brandau and Harrow, who show that for a Hamiltonian that has a degree D interaction graph, there exists a product state whose energy is within an error of order m, the number of terms in the Hamiltonian, over degree to the 1/3. So this says that the higher the degree of the Hamiltonian, the better approximations product states provide to the ground state. And there are other refinements of this theorem in their work, including efficient algorithms that actually output this product state in certain cases. So given this theorem, we can ask, to what extent can we improve on product states for these bounded local Hamiltonians by considering entangled states instead? So this is what we consider in our work. And we show that you can achieve extensive improvements over product state approximations for these bounded degree local Hamiltonians using a strategy based on applying low depth quantum circuits on these product states to make them entangled. So extensive here is a physics terminology. It means an improvement of the order of number of qubits or the number of interactions in these bounded degree graphs. So that was the first motivation for our work. Now let me tell you about the other one, about heuristic quantum algorithms. So as I mentioned, ground states of local Hamiltonians could be highly entangled states. And this motivates a potential application for quantum computers, which are good at handling entangled states. So as we saw in the previous two talks, quantum computers are good at simulating the dynamics of interacting quantum systems. And we are interested in understanding if they're also good at simulating the static properties of interacting quantum systems, including estimating the properties of ground states. And we are particularly interested in what these devices can achieve in some near future. And some near-term quantum computers can be modeled with low-depth quantum circuits. So we have n qubits, and we are applying multiple layers of entangling gates on these qubits. And we say the circuit, this quantum circuit, is low depth if the number of these entangling gates we're applying is small, which often, including in this talk, means a constant independent of the number of qubits in the circuit. So there have been many heuristic algorithms proposed to use these low-depth quantum circuits to estimate the properties of quantum systems, most famously variational algorithms that optimize the energy over the output state of a parameterized family of low-depth quantum circuits. So there are few known rigorous results about these algorithms, and this is another motivation for our work to find rigorous bounds on the performance of low-depth quantum circuits for estimating the ground state properties, or the ground state energy in particular. So to recap, we know many rigorous algorithms for estimating the ground state energy, output product states, and we'd like to know how we can improve them by applying quantum circuits on them. And I also told you about how many near-term algorithms are they use low-depth quantum circuits, and we'd like to analyze their performance rigorously. So answering these questions brings me to our first result. And as before, remember we have n qubits that are interacting with the Hamiltonian involving m terms, and each qubit has at most d neighbors. So given this, suppose we have a product state over these qubits, which has some energy variance defined as usual, given this quantity on the slide. Then given this, we show that there exists a constant depth quantum circuit U that when you apply on this input product state, achieves an energy which is improved compared to the initial product state with an amount proportional to the energy variance squared over degree squared times the number of terms in the Hamiltonian. And so this is the result. Now, let me tell you what it means more intuitively. So suppose the degree of the graph is fixed, it's just a constant. Then if the input product state has a variance of at least order m, the number of terms, and since the degree is fixed, just means a variance that scales with the number of qubits, then this theorem gives you an improvement of the order m in estimating the ground state energy, which is an extensive improvement, as I mentioned before. But if the input product state has low variance already, then it is already a good approximation to one of the eigenstates of the Hamiltonian. And in this case, we don't get any improvement. So a special case of this is the purely classical case, where we have a classical Hamiltonian, and the input product state is just a computational basis state. So as you might expect, that we don't get any improvement in this case. So the rough idea for the proof of this is the following. The circuit U that we apply in the previous slide consists of a series of commuting 2-qubit gates. And each of these gates is applied on one of the edges of the interaction graph and has this particular form in terms of some angles theta ij and operators pi. So these operators pi's are some Hermitian operators and designed such that when you sandwich them with the input product state, they just vanish. So our circuit is just these gates applied on all the edges. And as I mentioned, they commute, so you can write it as you see on the slide. And you can easily check that the circuit generalizes level 1 QAOA for this particular choice of operators pi. And we show that there exists an efficient algorithm for producing these angles theta and these operator pi's for any input product state and any Hamiltonian to get this improvement in the previous slide that relates to the variance. And the rough idea why this circuit might help you improve the energy is the following. So each of these 2-qubit gates is basically taking the product state across one edge and slightly rotating it towards the actual ground space of the Hamiltonian. So of course, one issue that we need to be careful about is that if we want to get an extensive improvement, we should be able to rotate a constant fraction of the edges in the graph. And it might happen that when we apply these gates on overlapping edges, we get a destructive interference and we get cancellations that makes it unclear whether we can get an order m improvement in the energy. But turns out if these angles theta are small enough up to the first order, these 2-qubit gates do slightly rotate their product states toward the actual ground space. So we show this by just basically like expansions around theta, and then there are some other steps that relate this back to variance that I'm going to skip. But this is like the basic intuition. Okay, so now let me tell you how we can improve our bounds in certain cases and its tightness. So one family of product states for which we can get a better bounds are locally optimal product states. And the reason we call them locally optimal is that up to first order, you can't improve or change their energy by applying single qubit gates on them. So this is given in this derivative being 0 condition on the slide. And for these locally optimal states, our improvement now is linear in the degree of the interaction graph compared to quadratic as I had in the previous slide. But the quadratic dependency in general is tight, and you can check that by this specific choice of one local Hamiltonians and simple input product state that you see. So this was all about when we want to analyze what improvements we get for a specific input product state. But we can also ask what is the generic performance of this circuit, meaning what kind of bounds we get when we randomly pick a product state as input. So before telling you the answer for that, I need to introduce a kind of a squared norm quantity of the Hamiltonian. So let's take the Hamiltonian and expand it in the Pauli basis. We get these f x y coefficients. Let's take the squared norm of these f coefficients. We get this quad of h quantity, which is like a quadratic norm of the Hamiltonian kind of. So given this, we show that if you randomly pick a product states as input, on average, you get an improvement that scales with quad of h squared over degree times n. So this is a generic performance for arbitrary graphs. But if your graph is assumed to be triangle free, meaning there aren't 3 vertices in the graph that form a triangle, then this improves to just a quad of h over a square root of b. Okay, so let me tell you how we can extend these bounds to the case that instead of a 2 local Hamiltonian, we have a general k local case. And now again, we can find a low depth quantum circuit that when you apply on input product state, it gives you almost the same bound as before, except that now the dependency on the degree is degree to the 4th. We believe with a better analysis, this should be improved to degree squared. But there is also an exponential dependency on the locality. There is a 2 to the k in the denominator. And one other extension is that so far I've been telling you about how we can improve the energy of initial product states. But we can also consider the case that we are given some already entangled states that we want to improve its energy. And this is one other thing to consider. So suppose we have some quantum circuit W with the depth D that we apply on all zeros state, and we get some potentially entangled state of V. So this is the input to our algorithm. Then we show there exists a quantum circuit U that, again, we can efficiently compute, that when applied on this initial entangled state gives you this improvement in the energy. So the difference between this and the product case is that now there is an exponential dependency on the depth of the initial circuit that prepares the input entangled state. So the more entangled your input state, in a sense, the exponential is smaller the improvement in the energy we get. So one difference between this result and the previous product case is that our circuit U is not constant depth anymore, and it has a different construction that I won't cover here. We can ask me later about it. We can also generalize this theorem to the case that the input entangled state is, instead of being generated by this circuit W, is the unique ground state of some gapped Hamiltonian. So in this case, instead of this exponential dependency on the depth, we get a polynomial dependency on the locality of that Hamiltonian. And this basically allows you to apply this theorem when you have a tensor or like a family of tensor network states as your input. And it's often the case that these are the ground state of gap Hamiltonians. All right, so that's almost all I wanted to tell you about. Now let me cover some open questions. So the first one is that what we're doing in this work is that it's kind of like a post-processing strategy when we are given some product state that some other algorithm generated, and then we apply a quantum circuit on top of that to improve its energy. But what ideally you'd like to have is an approximation algorithm that just naturally produces entangled states as output. And there are some family of approximation algorithms called STP relaxations that are widely used in classical computer science to solve the classical analog of estimating the ground state energy, which is solving constraint satisfaction problems. So these STP relaxations have been extended to solve or optimize quantum Hamiltonians. But as I mentioned, the output of these quantum versions is usually product states. There have been some progress, including a nice paper by Perek and Thompson that was covered on Monday. But in general, it remains open to take one of these STP relaxations and make them naturally output entangled states. This potentially improves upon our approach. One other question is whether similar strategies to what we use in our paper can be used to obtain circuit lower bounds for low energy states of local Hamiltonians. So right now, our improvements are related to the variance of these product states. If those could be removed, then via some arguments, you can take those improvements and turn them into circuit lower bounds. And finally, these results mostly talk about when we have a low depth quantum circuit applied on some product state. But at the end, what we'd like to have is a performance guarantee for the case that we are iteratively applying these low depth circuits on some initial product state, as is in the case in variational algorithms. So it remains open to obtain performance guarantees for this more general case. We do have results for entangled states, as I mentioned, but the circuit construction is not low depth. All right, so with that, I thank you for your attention.
Hi, really nice talk. Thanks.
Thanks.
You had this protocol for entangled states where you improved the energy using some efficiently constructible circuit, but then you had this factor that the deeper your circuit was, the worse the improvement was. Can you comment on sort of the fixed point of like the iterative application of this protocol?
Sorry, say your last sentence again.
Can you comment on sort of the fixed point of the iterative application of that protocol?
I mean, I guess if you just keep applying the same construction we have, you're adding a series of numbers that exponentially decay, so they converge to just something that scales the same as the first step. But this is our construction. It might be you might be able to devise like more clever ways to avoid this exponential dependency. We don't know if it has to be there or not.
I see. And as a follow-up question, I hope you don't mind. You talked about product states and how to improve the energy on product states. Have you thought about fermionic Gaussian states?
Yeah, that's a very good question. There's actually a talk on Friday by Matt Hastings, which is a joint work with Ryan O'Donnell. They consider SYK model, which is a fermionic Hamiltonian, and they have a sort of similar strategy to what we have, to take the equivalent of product states in their case, which is Gaussian states, and then they improve its energy by applying like a quantum circuit that kind of resembles what we are doing. And I think that might be what you're referring to.
Great, thanks.
Okay, great talk. My question is related to the previous question on the exponential dependence of the depth of the circuit for the entangled states. Can you comment a little bit more on if that can be improved, or where the limits are basically, if you're using, say, polynomial depth circuit?
Right. So, yeah, I don't know if it can be improved. I would guess not. I think this would be like a feature of these variational algorithms, that the more layers you apply, the smaller improvement you get. But whether it's actually exponential or not is something that that we don't prove, and I don't have good ideas for it right now.
Thank you.
Sorry, it's quite a vague question, but so these circuits work for low degree, and then for high degree, we know that product states are good. Do you have any idea what to do, like in the middle regime of like, yeah?
Right. Yeah, that's a good question. So you can take the degree in our work and just make it not be constant. You still do get bounds, but we don't use any structure that might show up in dense graphs. And there are known structures that have been used in other works. It's a good question whether you can find some other structure that you would see in those graphs and somehow use it to get better bounds than product states.
Okay, thanks.
So you have this nice result with triangle-free graphs. I was just curious about some of the reasoning that went into that result, and I was also curious if you considered whether that could be extended to graphs with only larger cycles, like where the minimum cycle was 4 or 5 or something.
So I guess the high-level intuition why triangle-free graphs give you a better bound is that the correlations that arise when you try to change the input product state is different when you have a triangle-free graph versus not, because you have in triangle-free graphs, by definition, you have a vertex that connects directly to 2 other vertices. So if you're considering strategies that you take those vertices and you try to change them to improve the energy, then you need to be careful how they interact with that common vertex they have. So if you eliminate them, then you don't need to worry about some cancellations that might show up. And I think we can get similar results if you consider the thing you mentioned, that it's a triangle-free graph. We have its generalization. We don't do it in our work, but maybe David knows better. But it might be possible. Yeah.
Thank you.
One quick question. So can we go to the previous slide? Yeah, so if you keep doing this procedure, can you just find the ground state, or will it converge to some other value?
So note that these are just, I have a constant factor here that I haven't been telling you about. So these are just the scalings. Ideally, what you would do is that you will optimize these angled theta and operators pi that I had before, which is the case in variational algorithms, to actually pin down this constant. And that's like the regime you would consider when you're getting to the actual ground state. You're just like talking about general scalings here.
Oh, I see. Thank you.
Okay, let's thank Mehdi and all of the speakers from the session one more time.
Thanks.